We're going to move on to section 4.2, which is now looking at areas. So what we did in 4.1 was we tried to reverse the process of differentiation, called anti-differentiation. This is instead looking at areas. So this is completely different. We're now going to be trying to figure out how do we find the area of things. Now we're going to be doing that with shapes that require us to use sums. So this video is going to be based on introducing sigma notation. So let's recall sigma notation. Maybe you saw this in high school, maybe you didn't. It's okay if you didn't. We're just going to get the hang of it. So with sigma notation, this is a capital sigma. This is going to indicate a sum. So this is a sum, but it's going to be written to help us kind of, instead of having a whole bunch of things added together, we can write it very succinctly. So to understand what this is saying, we have this I. This is going to be our index of summation. So I is going to start at 0, and it's going to go all the way up to 5, but we're only going to include the integers or whole numbers in between there. So what this is saying is that I'm going to say I starts at 0, but then I'm going to add on I when I is now 1, and then 2, and then 3, and then 4, and then 5. So this sigma notation is representing this sum over here of 0 plus 1 plus 2 plus 3 plus 4 plus 5. And you can add that together if you wanted to, but this is just helping us understand sigma notation. So instead, I is going from 1 to n in this case, and every time I start with 1, I equals 1, I'm going to add 1. When I goes to 2, I'm going to add 1. So in this case, I added new numbers because I was differing and I happened to be here. Here, I'm going to have 1 plus 1 plus 1 plus all of these. I have a whole bunch of 1s. Now, in particular, we know that there are n of these, right? Because we have the first one is from I equals 1, the second one's from I equals 2, I equals 3, and so forth till I equals n. And so this you can add all together to be n. So this one, now if we have I plus 1 over the square root of I goes from 1 to 3. That means I'm going to start by plugging in I equals 1 into this. So I have 1 plus 1 divided by the square root of 1. And I plug in the next one, I equals 2. So I have 2 plus 1 divided by the square root of 2. And then I add on when I get to the very last one, 3. I have 3 plus 1 divided by the square root of 3. So this is what the sigma notation looks like for this. Now here, k is going to start at 1 and go all the way up to n. Now n again is just some constant, we don't know, but it's just going to keep going on and on. So notice I have a 1 over n here. N is just some number. We don't know what it is. It's not changing. It's kind of like how 1 wasn't changing here. K is going to be changing, and that's it. So this is going to be 1 over n, and then we plug in 1 for k, so I have 1 squared plus 1. And then I do the next one. The next term when k equals 2 is going to be 1 over n times 2 squared plus 1. Then I go to the next one. When k equals 3, I have 1 over n times 3 squared plus 1. And I do this plus dot 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 thing, so we know that we keep adding on more things. It doesn't just automatically end there. We keep adding more and more of these until we get to the last term. Then we add the last term in. The last term is when k equals n. So this is going to be 1 over n times n squared plus 1. Now this one, we might have a subscript up here. So here, I is the variable that's changing, and I is going to be going from 1 to n. So only the subscript is changing. So what this looks like, this is going to be a sub 1 plus a sub 2 plus a sub 3 until you get to a sub n. And so this is what this sum looks like. And so this is going to be how we indicate just an arbitrary sum of a whole bunch of things. We're going to use this a sub I or a b sub I, but to just show that this is like the first thing, this is the second thing, this is the third thing, and so on and so forth. All right, so we're going to take a look at some properties of these. So in general, If a sub I is whatever it is, whatever we're going to be plugging in, that maybe depends on I. If we're adding a whole bunch of these, but there's a constant out in front, or constant in front of this, as you would expect based off of limits, derivatives, and anti-differentiation or integrals, I can pull out this k. So this is going to be k times the sum from I equals 1 to n of a sub I. So if we want to start to simplify these, we can pull out a constant in the front. Here, if we have the sum and difference, as long as this is a finite number and it's not going up to infinity, we can do the same thing that you would expect if we can separate this into adding and subtracting. So this will be the sum from I equals 1 to n of a sub I plus or minus the sum from I equals 1 to n of b sub I. So as long as n is finite, we can do this. Now, if we add a constant, so this is a constant, it's not going to change. We're going to be adding c plus c plus c plus c. How many times will we add c? Well, we're going to add it n times because we start at I equals 1 and we go up to n. There is going to be n copies of c, so that's going to be the same thing as c times n. Now, these get a little bit tricky. So this over here, when we add 0 plus 1 plus 2 plus 3 plus 4 plus 5, in this case, we would get, what is that, 6 plus 6, 15. Right, so we get 15. If I would have only went through 4, I would have gotten 10. If I only went, I goes from 0 up to 3, I would have only gotten 6. So this number is changing. And so there's a nice formula. If we start at 1 and we end at n, the formula that we have here is going to be n times n plus 1 divided by 2. Now, similarly, for I squared and I cubed, there's going to be these formulas, and you're just going to want to memorize what these formulas would be. So the formula for this is going to be n times n plus 1 times 2n plus 1 divided by 6. So this, and then this one for I cubed is going to be n squared times n plus 1 quantity squared divided by 4. And so these types of expressions are going to be appearing in a lot of the examples that we'll be doing. So we'll just want to keep these stored in the back of our brain. So this was just an introduction. We'll go through some examples to become comfortable with how do I start to use these to figure out a whole bunch of different sums.